In this video, we will work on solving word problems where we have to calculate the resultant vector of two vectors that are acting together. So, in problem number 4 here, Mitchell swims due east at a speed of 3.5 feet per second across a river directly towards the opposite bank. At the same time, the current of the river is carrying him due south at a rate of 2 feet per second. Find Mitchell's resultant speed and bearing. Okay, let's start with a diagram. Now, Mitchell starts off swimming due east across this river at a speed of 3.5 feet per second. So I'm going to draw a vector, right, representing Mitchell's speed and direction. All right, he's going due east, and I'll label the magnitude of 3.5 feet per second. Okay, so we've got 3.5 feet per second. Okay, so he's swimming across the river. Now, at the same time, the current of the river is carrying him due south at a rate of 2 feet per second. So now I'm going to put in a vector representing the speed of the current, the speed and direction of the current. So I'm going to make this vector a little bit shorter because it's not as fast. Let's make it a different color. Okay, and so this is representing the 2 feet per second speed of the current due south. Now, the actual speed and direction at which Mitchell will drift as he moves down and across the river is going to be the resultant of these two vectors. Now, if we add these vectors graphically, we are going to have a resultant that's going to go from the initial point of the first vector to the terminal point of the second vector. And I like to make my resultant vector green. So let's make that happen. Alright, this is going to be our resultant vector. Okay, so we need to find the magnitude and direction of this resultant. So first of all, the magnitude, that should be pretty simple. I'm going to call this vector R for resultant. Alright, I'm going to call this vector R. This is what we're looking for. So the magnitude of vector R is just going to be the square root of 3.5 squared plus 2 squared. That's how you do the magnitude. Okay, because really, look, in component form, vector R is 3.5 comma negative 2. Alright, this is the resultant vector in component form. It's right 3.5 and down 2. East 3.5 and south 2. Okay, so I mean, I guess technically if I'm going to look at it that way, maybe I could think of this as negative 2 squared to match what I'm doing here. Anyway, let's go ahead and find the magnitude of the vector. So as you can see, I'm getting 4.03. Okay, so that is the magnitude, is 4.03 feet per second. Okay, now how about the direction? I threw a little compass rose in here as a coordinate set of axes, and let's call this angle right here angle R for the reference angle that it is. And the thing is, the tangent of angle R would be 2 over 3.5. Okay, it would be 2 over 3.5. If I wanted to find the measure of angle R, I would do the inverse tangent of 2 over 3.5. Okay, so let's do that. Okay, so we'll do the inverse tangent of 2 over 3.5. Close those parentheses. Oh, you know what? I am still in radian mode. Let me switch over to degree mode and try that again. Okay, 29.74 degrees. Okay, so this angle R, the reference angle right here, is 29.74 degrees. Is that what it said? Yes. Okay, now we have to be careful how we say the direction, because there are many different methods that we have learned. We learned to measure angles counterclockwise from due east. We've learned to name angles in terms of how far they are away from one of the 4 cardinal directions, like 60 degrees north of west. And we've learned about this thing called bearing, where you measure clockwise from due north. So you got to be careful which one you're going to do. And if the directions give you any hint, you really have to pick up on that. So right here it says find Mitchell's resultant speed and bearing. So that word bearing tells us that we have to use this method called bearing, where we will measure clockwise from north, being sure to use 3 digits no matter what. Okay, so if we want to measure clockwise from north, we're going to have to take this reference angle that we found and add 90 degrees to it, because from north we have 90 degrees and then we have R. So, so the bearing should equal 90 degrees plus 29.74 degrees. So that's a bearing of 119.74 degrees. Now I'm going to write this up in a sentence or two. So the final summary is Mitchell is moving at a speed of 4.03 feet per second and a bearing of 119.74 degrees. Let's do another one. A glider is traveling at an airspeed of 15 miles per hour due west. If the wind is blowing at 5 miles per hour with a bearing of 060 degrees, what is the resulting speed of the glider? And they left out, they forgot to ask us for the bearing, the resulting bearing of the glider as well. So let's just add that on. And bearing. It's kind of like Edna Mode and guest. It's got to stick it on there. Now, a glider is traveling 15 miles per hour due east. So, due west. Let's go ahead and start our diagram. So this vector will represent the airspeed of the glider, 15 miles per hour due west. Okay. Now, the wind is blowing, well, let's label that. So that's 15 miles per hour. Now the wind is blowing at 5 miles per hour with a bearing of 60 degrees. So just real quick, when we talk about a bearing of 60 degrees, remember that bearing is measured from due north. So we need to visualize the cardinal directions, north, south, east, west. So when we say a bearing of 60 degrees, we're talking about 60 degrees east of north. All right, 60 degrees measured clockwise starting from north. So if I draw my vector for the wind, it's going to be something like this. And you need to understand that the angle, this angle right here, is the 60 degrees. That's the bearing. Okay, so fine, that's 60 degrees. The magnitude of the wind, the speed of the wind is 5 miles per hour. So let's label that as well. So 5 miles per hour. Now the resultant vector is going to look like this. Alright, just graphically, when we add vectors, we draw the resultant from the initial point of the first vector to the terminal point of the second vector. And let's go ahead and make it green. Okay, so this is what we are looking for. We want the magnitude and direction of this resultant vector, and I'm going to go ahead and call it R. Okay, let's make a chart. So here's what we're doing. We are basically given the magnitude and direction of each of these two quantities, the glider and the wind. We are going to change the magnitude and direction into component form so that we can easily add them. So let's take it piece by piece. Remember that the glider is this pink vector here, the 15 miles per hour due west. Okay, so let's talk magnitude, comma, direction. The magnitude is just 15. Now the direction, for the purposes of this chart, we need to use the direction method where we measure counterclockwise starting from east. We need to go back to that. Alright, because that's how our formulas are kind of built. So, in that sense, since this is going due west, alright, you know what, I feel like I should draw a separate little compass rose. Alright, if this is north and we're talking about a quantity that's going due west, okay, then the angle measured from east is 180 degrees. So magnitude and direction, 15 and 180 degrees. Now, what about the wind? The magnitude of the wind is 5 miles per hour. That's just the speed. Alright, that part is easy. Now, what about the direction of the wind? So again, I feel like we should draw ourselves a new little diagram, a new little compass rose. So here's north, and our wind is blowing in such a way that it's here in the first quadrant, and this angle way up here is 60 degrees. But the direction that we need for the chart is the good old direction measured from east. So if this is 60, then this angle, the reference angle here, must be 30 degrees. So that's what we need for the direction of the wind. Alright, so we have the magnitude and direction of each. Now, we are going to turn these into component form using the following formula. If you have the magnitude and direction, and so you see the r comma theta that I wrote before. If you have r comma theta, the magnitude and the direction, the component form is going to be r cosine theta, comma, and then r sine theta for the horizontal component and the vertical component. So for the glider, r cosine theta is 15 cosine 180, and r sine theta is 15 sine 180. For the wind, r cosine theta is 5 cosine 30, and r sine theta is 5 sine 30. So we'll just put these in our calculator and turn them into decimals. I'll do one of them on camera and I'll do the rest off camera. So we have 15 cosine 180. So we just write 15 cosine 180. Alright, well that's just negative 15. Alright, which makes sense, and we really didn't need to do the calculations to know that in component form, if you're looking at something that's going due west, that's going to be, it's just going to be negative 15, and then this one's going to be 0. Right? Because it's only going to the left. It only has a horizontal component. There will be no vertical component. I mean, you could type it in your calculator if you want to feel silly. Go ahead and type it in, 15 sine 180. But when you see that the answer is 0, you're going to think, oh man, I knew that. There's no vertical component. Of course it's 0. Why did I type it in my calculator? Similarly, on this side, we're going to do 5 cosine 30 and 5 sine 30. So 5 cosine 30, and that's going to be 4.33. And now 5 sine 30. And that's 2.5. So for the resultant vector, which we'll do the calculations for the resultant over here, resultant. All we have to do is add these up. So we'll just add the negative 15 and the 4.33. So that's negative 10.67. And then of course 0 plus 2.5 is just 2.5. Okay, so we put them into component form so we could add easily like we just did. So now we have the resultant vector in component form. All we have to do now is turn it back into a magnitude and a direction. So look, we know how to calculate the magnitude. Let's do that here. when you calculate the magnitude. You just do the square root of negative 10.67 squared plus 2.5 squared. I'm just going to put this in my calculator. So here I've typed it into the calculator. Alright, so the magnitude is 10.96. Okay, so 10.96 miles per hour. Alright, now let's talk direction. So for the direction, I recommend making a little diagram always. Okay, so we have so there's north. So if we have negative 10.67 and positive 2.5, what quadrant is that going to be in? Alright, hopefully you can see that we are talking about the second quadrant. Alright, we're dealing with a vector that looks like this. If I make a little triangle out of the reference angle, alright, and so this is left 10.67, so there's my 10.67, and is up 2.5, and obviously my drawing is not to scale. If I want to find the measure of this angle R, I'm going to say that the tangent of R is equal to 2.5 over, now normally I would say negative 10.67, but all I care about is the positive value of R, so I'm just going to put positive 10.67. So therefore R is going to equal the inverse tangent of 2.5 over 10.67. Okay, let's see what that is. The inverse tangent of 2.5 over 10.67. So that is 13.19 degrees. Okay. Now, if we measure this as an angle that begins from east, then we would have to do 180 degrees minus 13.19. And normally when we're doing a chart like this and we're doing r, comma, theta, magnitude and direction, this is the kind of the direction that we use. We just measure from east. So let's start with that. So if we do 180 minus 13.19, that gives us 166.81. Okay, and that's the theta when we talk about r, comma, theta, magnitude and direction. Okay, so let's just record all of that on our chart. So the magnitude was 10.96 and the direction is 166.81 degrees. Okay, now, so we could call ourselves finished having found the magnitude and direction of the resulting speed of the glider. But they did mention the word bearing. So since they're giving the wind direction in terms of bearing, then for our final answer, we should probably give the direction of the glider, the resulting direction of the glider, as a bearing. All right, so let's take our 166.81 degrees and let's instead think of it as a bearing. So remember that bearing is measured from due north, and you measure it clockwise. So the question is, how far is this vector if we go clockwise from north all the way around? Because that would be the bearing. Okay, so let's see. If we had stopped here, that would have been a bearing of 270. All right, we've just sort of memorized that if we go 3 quadrants, that's 270 right here. But we went 270, and then we went this distance of r more. So if we're talking about bearing, the bearing is going to be 270 degrees plus what we got for this r, 13.19. So that's 283.19 degrees. That is the bearing. Let's put that all together in a summary sentence. So here's your final summary statement. The resulting speed and bearing of the glider are 10.96 miles per hour and 283.19 degrees. Let's do one more problem. Sonia is swimming due west at a rate of 1.5 meters per second. A strong current is flowing south 20 degrees east at a rate of 1 meter per second. Find Sonia's resulting speed and bearing. Let's make a chart and organize our work. We have Sonia, we have the current, and then we have the net result of the two. So for each quantity, we're going to record the magnitude and direction. And what we're going to do is convert that into component form so we can add and create the resultant vector. And then we will convert that back into the magnitude and direction. So let's start with Sonia. She is swimming due west at a rate of 1.5 meters per second. So look, the magnitude is simply the 1.5 meters per second. Now let's talk about the direction. If she is traveling due west, okay, and the magnitude is 1.5, when we talk about the direction, think about where this would be if we measured it from the positive x-axis. Okay, so if this is north and this is east, if we measure this direction starting from east, you can see that we are talking about 180 degrees. So that is the theta that we're going to use when we talk about magnitude and direction on this chart. So magnitude 1.5, direction 180 degrees from east. Okay, now let's talk about the current. All right, the magnitude and direction of the current. A strong current is flowing at south 20 degrees east at a rate of 1 meter per second. Well, let's get the easy part out of the way. The magnitude is 1. Okay, now let's talk about the direction. So let's make a little diagram for this. All right, here's north. Now this notation, south 20 degrees east. When you read something that's in that form, it's literally giving you directions. It's telling you where to look first, and then sort of where, how far to turn your eyes and which direction to look. So when it says south 20 degrees east, that means start by looking south. which would be right here, but then turn 20 degrees towards east. So we started south, but then we're going to turn 20 degrees towards east like this. So that means this is 20 degrees right here. However, for the purposes of the chart, when we record theta, we need the type of direction that's measured from the positive x-axis, measured from east. So we need this angle shown here. So I just went through a full 3 quadrants. If I had stopped at south, that would have been 270 degrees. But I kept going an extra 20 degrees. So of course 270 plus an extra 20 degrees is 290 degrees. So when we record the direction on this chart, that's what we're going to put, 290 degrees. So we have the magnitude and the direction for Sonia and the current. Now unfortunately we can't just add these together for the resultant. For that we need component form. Now remember, if you have the magnitude and the direction, r and theta, component form is going to be r cosine theta, comma, r sine theta, the horizontal component and the vertical component. Now, when you're talking about a direction, something that's traveling in a direction that's due west or due east or north or south, you don't have to use this little formula. So Sonia was swimming due west. Because she was just going only west, that is, in component form, that would be negative 1.5, which means you're going west 1.5, and that's it. That's the end of it. There's no other component. There's only a horizontal component, and it's negative because it's going west. There is no vertical component, so we're going to put 0 for the vertical component. Alright, so notice we don't need to do r cosine theta or r sine theta if it's a quadrantal angle like this. But for the current, which is not on one of the cardinal directions, north, south, east, west, this is when we will do r cosine theta, r sine theta. It'll be a little bit easier because the radius here is 1. So when we do r cosine theta, for example, it's just going to be 1 cosine 290. Okay, I didn't really even need the 1. And it'll be 1 sine 290. So we could just put that in the calculator. That turned out to be 0.34 comma negative 0.93. Now the point of putting these both in component form is so that we can add them together and find the resultant in component form. There's no way we can easily combine these when all we have is the magnitude and direction. But in component form, we can just add the corresponding parts. So if we do negative 1.5 plus 0.34, we're going to get the horizontal component of the resultant. That gives me negative 1.16. Now, of course, if I add 0 and negative 0.93, that's just going to give me negative 0.93. So now I have the resultant in component form. Now let's turn that into magnitude and direction. The magnitude is very straightforward because all we have to do is use the magnitude formula. So I will do negative 1.16 squared plus negative 0.93 squared. and I'll just put that in the old calculator. That gives me 1.49, actually, need to round that up, meters per second. And let's go ahead and put that back in the chart. Now for the direction, I recommend doing a little sketch. Let's get a coordinate axis going. Okay, here's north. And now looking at the components, we're going left 1.16 and down 0.93. That puts us in the third quadrant. So let's just draw our vector going into the third quadrant like this. Alright, let's go ahead and find this reference angle by making a little triangle out of it. And it was left 1.16 and then down 0.93. So if I want to find r, I could use tangent. So let me just skip to the part where we say the inverse tangent. So the measure of angle r is going to be the inverse tangent of 0.93 over 1.16. That's 38.72 degrees. I just put that in my calculator. Now that's just the reference angle. When we talk about r and theta, and we're doing this chart, magnitude and direction, we are measuring from due east. So the actual direction theta should be 180 degrees plus the r, plus 38.72. And that's 218.72 degrees. So I'm going to go ahead and record that on my chart. 218.72 degrees. So we were supposed to find the resulting speed and bearing. What we have right now is the resulting speed, 1.49 what is this, meters per second. Okay, I'll go ahead and put the units, meters per second. And we have the direction. But we're not quite finished because we're supposed to give the bearing. And remember, right now we're giving the direction as our standard measured counterclockwise from east, like this. But bearing is measured going clockwise from north. So we just need to do that one more translation and ask ourselves, for bearing, what would the angle look like if we went clockwise from north around to this angle? Okay, and notice we were on our way to 270. If we had gotten all the way to this quadrant, right, if we had gone all the way around to west, that would have been 270 degrees. But we had to stop short. We had to stop short by the amount of r. So the bearing, which is what they really asked us for, should be 270 minus the r. So 270 minus the 38.72. And that is 231.28 degrees. That's the bearing. So, time to make our summary statement and then we'll be done. So the final answer is Sonia's resulting speed and bearing are 1.49 meters per second and 231.28 degrees. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video and click over here to subscribe. That way you'll get every new video delivered right to your home screen.